When data people get together, they often bring up a statistic. 80% of our time is preparing and organizing the data. The other 20% of the time, complaining about the 80% of the time. So I'm going to be talking about the complaining part. This is the pipeline that data engineers and data scientists work with. Acquiring data, getting it, ingesting it, making some sense of it. Finally, there's the exploration, analyze, and then you present it to folks. It takes a lot of tools to get this to happen. At the big social media companies with a lot of data, they use a lot of these different things. It's a lot of hard work. And these are the roles that people are involved with, what they might call themselves in here. What I want to focus on a little is this part, and something that's primary to this. And so I'm going to bring up someone who should be a legend, someone who, if you know Edward Tufte, said should be compared to Galileo. His name is John Twokey. He was a statistician. His kind of heyday was from the 40s till he died in 2000. He coined the word bit. He coined the word software. He vetted the Kinsey sex data work when there were some questions about his data. He did work that led to the U-2 spy plane. He predicted the first election with computers when Kennedy beat Nixon. He invented fast Fourier transforms, which is how we all have MP3s. It's something that turns analog to digital data. Most importantly, he said exploration is far more important than confirmation with data. And what does that mean? It means when you build a model, which is confirmation, which is what the pharmaceutical companies, which drove a lot of early statistical work, focused on, was a very small part, in that you really should look at the bigger picture of exploration, and that visualizing was very important. So in the 40s and 50s, he had T-squares and Bezier curves and stuff, and was doing graphics at that time, and very effectively. Okay. So exploration, what does that mean? It tends to be things around histograms or scatter plots. You can get these in Excel. Frequency distributions, which is just a list of what you have and how often they occur. And you're looking for patterns, and you're looking for outliers. And that's a critical part of what's going on, and I'll show some of that in here. And at the top is a histogram, the bottom is a distribution that I'll be using later here. So I mentioned these three parts, and this is where you want to go in and do exploring so that you can start with the cleaning, standardizing, and normalizing. The skills people need to do this, and this is why data can be kind of tough and why you need data engineers, are parsing, separating pieces of the data out, using regular expressions, which is patterns that appear in language that let you pull things out. You're going to probably have to do stuff manually. You're going to have to clean things with people looking at it. You can crowdsource to help you. Luckily, you can also use machine learning, which is really pretty good. Integrating the data is also really important, and that's that you want to bring all the like things together, and you want to connect the people, places, the times, and so forth that you're working on. Now, I know that I'm the only Roger Magoulas in the world, but these are all the emails I have, and all the ways I kind of identify myself online. To bring all that together can be really hard work and require some manual work, but without that, you tend to get your data unreliable. Okay. Whenever you work with data, unless you have a very small data set, you're going to have to put it into some kind of bucket. You're going to have to do something with it that lets you make sense. It's usually going to be hierarchical. You're usually going to do that multiple times. And I don't know if orthogonal, but everyone knows what that means. It literally means right angles. But you're probably going to have things that categorize things in different ways. And one of the, I'll just use cancer, which used to be mostly identified by where it is in your body. But now they realize through genetics and other things that a lot of cancers that are in different parts of your body are actually the same thing. There's also what stage a cancer might be in. So there's just 3 orthogonal roll-ups that you might have around a disease study. Okay. I'm going to go, Juliet talked about going deep, and I'm going to start talking about statistics. So who is this handsome young man? His real name is Iosif, let me get this right, Djugashvili, who you might know as Joseph Stalin, who had this to say when he was commissar of munitions during the Russian Revolution: a single death is a tragedy, a million deaths is a statistic. So why do I bring this up? Juliet brought up bringing the human part into data, and we can use these kind of statistics to help us get there. So this is just some data. It's there. If you wanted to try to make some sense of it, the first thing you might do is a mean or an average. Just take all the numbers, divide it by the number that are there. You come up with 11.1. If you order the data into a frequency distribution, the other thing you can use is a median, which is the value that occurs in the middle. Happens that I have an even number of things, so it's right between those two, and that's at 11. They give you about the same number. So why do we have these two different measures? Well, mostly because in the real world, there are outliers. And two places where this is really common is with housing prices and with incomes, because there's a Bill Gates or there's a house, a mansion someplace that can pull things off. If we did the average, it's around 19.34, which with the original data is right near the top of that. But the median, after you order things, brings you right back to where you were before. So this is one of the ways to handle the data. I'll just bring the mean back in there. You can also just remove the outlier, but depending on what you're looking at, you may or may not want to do that. The last measure is called the mode, which is the thing that occurs most frequently. In this case, the value 12 appears 3 times in the data set I showed. Now, there could be multiple of these, and this is one of the patterns you really want to look at. So these things are around averages, but this is another thing statisticians say, is that average companies use averages. And that's because there's some assumptions around averages that hold. So this is called the standard distribution or the normal distribution, bell-shaped curve. A lot of things in nature and around, like things failing work with this. And the statistics work pretty well with this. Here's 2 separate distributions. One is tall and kind of thin. The other is flatter. And what happens with this is you can look at the averages of these, and you can see the blue line is to the right, has a higher average than the red one. But if you look at this closely, you'll see that when you look at the tail over there, the blue one is higher over it. Now, there was a study done on how people sleep and their socioeconomic status. And 2 researchers got into an argument about this. One had that poor people tended to have the blue line kind of thing, this kind of flatter distribution, that they slept more. And the other researcher said, no, they sleep less. I see this big group down here in the kind of shady area. In a way, they're both right. And that's why, going back to what Twokey said, visualization really matters. Now, here's another frequency distribution that shows something that's commonly called the power law or Pareto Rule, which is that often a few things are responsible for most things. This happens to be book sales by language, which is something I'll go to a couple times in here. The top 10 languages are responsible for 80% of the sales, and then everything else is the long tail. And this can help you make decisions about stuff. Even if you kind of knew that by looking at the numbers, it's so much better to be able to look at the chart of this stuff. Now, this is a chart similar to one that Juliet showed. And I think whenever you're showing data, particularly if you're showing rate of change, you really need to show the magnitude, because that matters a lot in how you interpret what's going on. In this case, I've got magnitude on the left, and I've got the rate of change on the right. Swift is a language that only just came out, and you see it kind of pegs out there at 100%. Because it's a new language, it was actually at 0 before, and the real value would be infinity, but it's hard to show infinity on the chart. But I was able to have a value that let you see that it's growing big. But you can see that if you're looking at this and deciding what to do, Swift is growing very rapidly, but from a small base, and Python is also growing fast. You can, again, adjust your what's going on. Context always matters in this stuff. And if you see, I have what all book sales are doing. So you can now compare what's going on in the topics you're looking at with everything. In this case, all is down -1%. Average companies use averages. This is one of the reasons why. This is known as Anscombe's quartet. These sets of data all have the same mean, the same standard deviation, and the same linear regression. But you can see the data looks really different. And if you didn't look at it, you wouldn't notice that. In this last case, that yellow point is an outlier and might be something that you wouldn't want to look at. Okay, linear regression. If you've read Freakonomics, irrationally predictable, and a couple other books. This is what a lot of social scientists use to work at things. I'm just going to show binomial. There'll be a quiz on binomial later. Two values. These are two data sets, again, from that programming language stuff. You can just go into Excel, pull down, add trend line, and in fact, I added the formula, and you get the linear regression on it. Now, this one, for Java, is pretty flat, not much going on. But the big thing is this R squared. You don't have to know really what R squared is. It's kind of a measure of the fit of the line. That's a very poor number. R squared goes between 0 and 1. The closer to 1, the more it explains. This one, very little is explained by the chart. Now, Python actually has an R squared of 0.6, which is pretty good. And that means it's more reliable. It explains, time explains more of what's going on. So again, you can base your decisions at the data on how reliable the trend line is. Okay, I'm going to get into a little hairy stuff here with this guy, Karl Popper, who basically was able to, in a way, articulate the scientific method with this notion of the null hypothesis and falsification. It is very difficult to prove something is true, right? Which is called, let me make sure I get it right, is induction. It's very hard to do, but deduction, which is trying to say that there's something isn't true, and it's very unlikely that that would happen, is a vote for the hypothesis you have being okay. Now, I know I didn't say that very well, but it's like you're making a bet against yourself with a null hypothesis. And if that bet against yourself is really rare, and the two values people use are called t-value and p-value, you can say, well, I think I have more confidence in my real hypothesis is true because the false one isn't there. The next one, and this one will really be a quiz on. I'm kidding. This is Bayes theory, Bayesian probability. I only bring it up because this represented a change in the way people look at data, and it's mostly around being able to iterate and using the data that matters. There's evidence, and there's what happened in the past. You bring those together, you can keep learning. And a lot of machine learning is kind of based on the same process. So we'll talk quick about machine learning. The two main things people do with machine learning is this techniques really, supervised and unsupervised. Supervised means you kind of know what you want, and you're going to do some training. You're going to use that training to develop a kind of a model that you apply to all your other data, and then assignments come, and you can look to see how accurate it is. The unsupervised is you just give a bunch of data to an algorithm, it tends to do something with it that puts it in some kind of groups, and you decide, is this worth anything? Am I finding something I didn't really know? The accuracy tends to be lower, but it's good for exploration. There's other things you can do around recommendation engines, and of course, this is the basis for when we bow down to our robot overlords. They'll be using this style stuff. Now, in my work, I do a lot of categorization and clustering. Categorization is just putting things into categories, and clustering is grouping things into ways that you can maybe take some action on. So here's a couple of examples. The first is, in the US, there was something called the High-Tech Act. It put electronic medical record systems in all healthcare providers, and they want to know if that created jobs. I have a jobs database. It's got 2 billion jobs in it. It's really hard to work with. The data is a mess. It's terrible to look at. It's hard for a human to process too much of that data. So we needed to identify the new jobs that were created by the High-Tech Act, which is around installing and doing stuff around the electronic medical records. We had a lot of challenges with it. I'm not going to go through all these in detail, but we were able to train a set of jobs, figure out whether they were or weren't EMR jobs, build what's called the Bayesian naive Bayes model, and come up with this. And we ended up having very high accuracy. We categorized 400,000 jobs, which no human could have done, or even a group of humans could have done easily. And in fact, it did create jobs. The red is the EMR jobs, and this is all normalized to 100 in the beginning period. And the green is all jobs in the economy. And you can see that the red shows up much higher there. We run a conference called Strata about data. I became the chair of the conference right when we were moving from London to Barcelona. And we're like, wow, we've been doing in London for a while. How are we going to get people to go? So we really want to identify where data people were concentrating. But how do we get that data? We didn't really have any access to it. The London one, about half the audience came from the UK, so we didn't have that much data from elsewhere. So we went into Meetup. because people show their intention in Meetup. And we were able to do their API and identify, we went all over Europe and extended it out a little bit, find all the data meetups, look at how many people attended in the last 6 months, and started rating them. And what we found was the cities where there were some meetups happening, and then how many were attending. And this was really valuable for us. Like Tel Aviv, we extended our marketing to Israel, where we probably wouldn't have before. Stockholm came out very high. We were able to then make our marketing efforts around folks more efficient by looking at this data that wasn't ours, but was just available in the world. I just wanted to show a clustering that we did. This is around a data science survey that we do, and it helps us to see how the tools group together. And the actions that you can take on this are around, because I run another conference, is how do we organize the content, and how do we even organize just our books to focus on the audience in the right way. So I've been talking about data. We also, and as Juliet was talking about, think about qualitative data too. And we did a study that looked at how developers learn. There were things going on in what we were doing that we didn't think we really understood, and we were able to get some information from that helped us figure out something we didn't really know, we couldn't have found in the data, which is around like things like training budgets and the breadth of things people needed to know and so forth, that we could then instrument around. So we kind of built a loop around qualitative to quantitative information. Okay. So we've been talking a lot about the tools you use in data, but really the important part is that it's humans that are involved, and we're often looking at human behavior. And humans are a mess, right? We're irrational, we construct our perception. So a little example of that. This book here, which you can download, came out of the CIA, and was actually about how to handle what they call open source, which is different than my open source, which is spies. And there's a lot you can learn from that, but here's a quick experiment. Something didn't. Okay, there's a font issue that didn't show up. So the experiment will go right into World War II. The statisticians at Columbia were brought in to help with problems during World War II that the military was having a hard time solving. One of them was that bombers were not coming back from missions, and they had this data where the planes were getting hit. So planes would come back, they'd note where all the bullets were. They built these kind of visual models which were really effective, and they were going to armor where the bullets were going to hit. This is what the Air Force was going to do. And armor is a kind of a double-edged sword, because the more armor you put on, the less good your plane is. It's heavier, can't fly as high, and so forth. And then this guy came on the scene. His name is Abraham Wald, and he said, well, the place you should armor is where the bullets aren't. The place is like near the wing there and stuff. And the Air Force was like, what do you mean? He said, well, you measured the planes that came back. Those are the planes that can survive the bullets. The ones that didn't get back were likely hit in those other places. So survivor biaship, like everyone here who reads a How to Be Successful in Business book and thinks they can extract something from that, you're only looking at the successes, and without factoring in the failures, you really are missing a lot of data. So how do you handle cognitive bias? We all have it. We all have our own frames. Well, just being aware is really the most important part. So just that you know what's going on. Understand that your own personal experiences are going to weigh way higher than things that are extract, going back to Stalin. When you know something happened, you're going to be just more sensitive to what's going on. Missing data, like failures instead of just successes. If you start looking at stuff quickly, your initial impressions are not what should come from looking at everything. And think about probability. When does water boil at? 100 degrees centigrade? Well, we're all breathing moisture-filled air, so there is H2O in a gaseous form right now. 100 is a probability that most water will turn into a gas. Keep that in mind, because hardly anything is truly binary that's there. Being open is really important, and knowing that when you have a lot of information, you're going to have a hard time digesting it can help you track things. Okay. More and more people are getting access to data, and that's a good thing and a bad thing. And the bad thing is that it kind of can suck a lot of energy out of an organization. People have competing results and stuff. A way to handle it, and this reinforces something Juliet was saying, is around collaboration. If you've got an analyst isolated, they're just going to what's called regress to the mean. They're not going to get better unless they're getting bounced off other people and able to test their ideas and be challenged on it. You really want to do a couple things to make sure that everyone understands how good the data you're working with is, knowing where it came from, what time it happened, being able to reproduce what was going on, knowing that your analysts might be able to do analytics for you that will help because they have been looking at everything, where organizations tend to be a little myopic, using stories to tell about the data, and letting the stakeholders in that story because of their domain expertise. Now, the main driver, I think, behind all this is curiosity. And I won't go into the detail here. Beginner's mind is probably the most important part of this, is just trying to look at something as though you never looked at it before, right when you start, to help you get to the right questions. So, in summary, if I didn't say visualizing data isn't important enough, I'll say it again. It's really important. It's the best way to explore the data. Think about asking the right questions more than precision and what tools you're using. Think about what's missing, because it's really easy when you're in the data to think, this is my world, and forgetting something that you couldn't get that's really important outside. Don't forget to collaborate in every aspect of what you're doing. We're all biased. We need to handle those biases and keep curiosity in the game. Be curious, want to know what's going on. The best analytics ask more questions than they answer. If you do all that, you can get into a state of bliss, a data bliss. And that's the end.
Thank you. Thank you.